Okay. All right, we're going to give this a try. Oh, yeah. Okay. My surface might not project, but the dot cam can look at my surface. Okay. Is this legible at all out of pure interest? Okay. All right. We're going to try. Okay. So we have an AVL tree here, and we are told we need to insert the number 55. Now, the question read, what will be the parent of the 55 after insertion but before any rotations? Does anybody want to offer their guess as to where 55 is initially going to get put into this tree? All right, of the 51, so right here. And the reason that we're putting it there, right, is that we're going to come down and we're going to say, hey, is 55 greater than 42? Yep. Is it greater than 47? Yep. Is it less than 63? Yep. Greater than 51? Boom. Now, and a bunch of people asked me this after class on Friday, which is great. The way that we implement AVL trees is we're actually going to store the height of each node inside of itself. That's one way to do it. There's other ways to do it. So right now we're going to say like the height of this is 0, because remember a node by itself has a height of 0. And so then when we recurse back up, previously the height of 51 would have been 0, but I know that by adding in something, I have to go from 0 to at least 1. So that height will get updated to 1. Now that I've done that, I'm going to continue up. And previously, the 63 would have had a height of 1 because of 51. But we're going to update that height to be 2. However, 63 has its left tree has a height of 2. But its right tree has a height of -1. -1, because there's nothing there. So 63 becomes imbalanced. Is it imbalanced or unbalanced? Imbalanced? I don't know. English doesn't make sense. Even for those of us that are supposed to know it. And then as you can imagine, we continue up. Now this subtree has a height of 2. This previously had a height of what? It had a height of 0 there, and it had a height of 1 over there. But now it's got a height of 2. Boop, boop, boop. Is 47 balanced or imbalanced? Imbalanced. I agree. And then we come back up, and 42 originally had a height of, what was it, 1, 2 would have been its longest, but now, instead, it's got a height of what? Good question. Ooh, good question. So let's see. Yeah, so 1, 2, 3, 4, right? Is that correct? Yep. Okay. And that's compared to what over here? So what's going on? Imbalanced or imbalanced? Imbalanced. So 63, 47, and 42 become imbalanced, and it becomes the child of 51. Now, if you remember, the way that we deal with these things is we sort of put them in and then we go back in. What we would do is we would balance these bottom 3 here. And so what would happen, remember, is that this is the kink case. And so that means that we would have to rotate to get to the line case. And then we would rotate again. And then we would end up with, what would we end up? I'm trying to sort of like draw on top of these things. The overall root would become the 55. And then it would have the 51. And then it would have the 63 there. And then we would sort of rotate our ways back up. I'm not going to draw all of it because I'm not going to make all of you draw it, but that's just sort of an idea of how that insertion and that recalculation of heights might go. Technically, we wouldn't go all the way up and recalculate this height. We technically would come up and calculate this height, and at that moment, we'd be like, woo, imbalanced, immediately handle it, do the rotations right then and there. And in doing so, we might need to adjust our height, right? Like, hopefully, when we rebalance, our height might shrink again, so we don't have that disparity. And so in that context, then we don't have this sort of like height of 2 anymore, right? We would just have the height of 1. And in that case, would we have to do any more rotations? If the only rotation I did was to fix this down here, would 47 and 42 still be imbalanced? If it helps, it would look like this. Right? This is no longer imbalanced here. Is this still imbalanced? Is this still imbalanced? So let's see. So 47, yeah. This has a height of what? 0. This is a height of what? 1. Balanced. This is a height of what? 2. This is a height of 3. We're okay. So technically, we only had to do 1 rotation to fix this tree. It technically caused the imbalance all the way up, but yes, question? 2 rotations, sorry, yes. The 2 rotations meaning to fix this little subtree, because you're right. One of them was a double rotation, which came from this here. Yeah? Again, I'm not going to make you draw out the rotations, but I just wanted to give you an example of how effective this actually can be, because though things became imbalanced, just that singular fix at the moment that we created it, we didn't have to worry about any of these things anymore. Yes, question?
Just to clarify, is the counting of height relative to a specific node? Like we could, count from 63, 51, or 42? Or is there like a specific convention that we count from bottom to top?
Like when we were determining the imbalanced moments?
Yeah, the height.
So we always count in terms of this. So like the height of 42 was 4, and now it's 3, right? Because of how I changed this tree. And so we always talk about it in terms of like each individual. So like this 47's height is what, there we go. And sort of 55, that height, so on and so forth. So we always talk about it in terms of the individual nodes. The key is that, remember, this is going to be recursion. So the way that this kind of works is I'm recursing left and right down. At the moment that I get to a spot where there is space for me, then I place my node, and it's only at that moment that I start to ask myself, as I kind of like close that recursion loop back up, as I'm sort of like finishing those recursive calls that I opened to make my way down the AVL tree. After I place it, those recursive calls have to finish, and they kind of close their way back up, right? So it's sort of like I opened a recursion left here, and then I opened another recursion. Whoops, sorry. I can tell my left and right sometimes. So that like opened one, and this went right, so that opened one, and then previously or whatever, I opened all those things. And so as I'm kind of coming back and closing those recursive loops, that's when I'm doing that evaluation of the height and any rotations and things like that, so that by the time I get all the way back up and I've closed all of my recursions, I've done all of my rotations and cleanliness. Let's see. And then I do this. Okay, that kind of worked. All right. I will not be bested by technology. We made you technology. You must listen to us. Okay. Good try. Okay, so I just wanted to wrap up some of the conversations we had around AVLs, but we're actually diving into yet another new topic today. So reminder that there are 2 general cases of imbalance. There's the line case and the kink case. The line case takes 1 rotation to fix. The kink case takes 2 rotations, where you first rotate into the line case and then you rotate from the line case into balance. So for example, as you can imagine with this kink case, you would rotate it this one here, so that it looked like this one. So you would rotate that 2 and 3 so that you had that 1, 2, 3, and then you could rebalance it, and 2 would become the root of those. So this is the conversation I wanted to make sure that we had. How long does this rebalancing take? So we know that the number of recursive calls is going to be however tall the height of the tree is. And so how do we find an unbalanced node? Unbalanced node? Is we just kind of end up recursing back up. And like I mentioned, I don't think I said it in class on Friday, but a lot of good questions. One way to do this is to just add an extra field to each node that keeps in mind the current height. And then as you sort of close those recursions back up, you can look at your children's height field and update yours accordingly, right? Because your height is the height of your tallest child plus 1, right? Because you're 1 above your child. And so the question then becomes, okay, how we can tell whether something's imbalanced by the sort of recursion from the top and back, from the top to the bottom and back up. So that's that logarithmic time to get from the top of a tree to the bottom. That takes log n. From the bottom of the tree to the top of the tree, that takes log n time as well. But how many rotations might we have to do? So we just have to do a single or double rotation on the lowest imbalanced node. A rotation will cause the subtree rooted where the rotation happens to have the same height as it had before the insertion. So at most, I'm only ever going to have to do this single or double rotation. And so we only have to take logarithmic time to get down to the bottom, logarithmic time to get back up the top. And those rotations, they are only ever really looking at that sort of like small subset of nodes involved in the rotation. Remember on this slide, right, we're just looking at sort of like 3 nodes at a time. So as it turns out, it's actually constant time to do the rotations, because we're only ever really looking at the rotation of 3 nodes at a time. 3 is some number independent of n. So to change the pointers in that little cluster of imbalance, that is independent of however many nodes are elsewhere in the tree, right? Like I don't care if that imbalance, it happened on the leaf of a tree with a height of 3, or it happened on a tree with a height of 300. As long as I'm maintaining the balance the entire way through, then every new imbalance moment is only ever going to trigger those 1 or 2 rotations, which are some constant amount of just pointer swapping independent of n. Which is absolutely amazing, because then that means that this AVL tree implementation guarantees a log n runtime for any puts or any adds. So if we're using a map ADT, the put is guaranteed to be at worst log n. I think, sorry, figuring out how to actually navigate this. Oh, here's more details on how the insert works. You're welcome to read this as much as you want. There we go. Here's some basic stuff on delete. This is literally, this isn't just me deleting this for this quarter. We've never really taught delete. Delete's really complicated for AVLs, but I can tell you that its worst case is also log n. So that takes us to the final slide that I wanted to make sure we talked about with AVLs is the pros of an AVL tree is that we have taken the goodness of that binary search functionality and totally eliminated any of the case that would cause that degenerate tree. So we are now guaranteeing our tree will be balanced. And because we're guaranteeing a balanced tree, we are guaranteeing that logarithmic worst case runtime, especially because we just determined that the rebalancing is a constant time function. So pretty positive. You'll find that AVL trees and self-balancing trees do come into practice in a good amount of industry scenarios. A lot of times, like I sort of mentioned when somebody was asking about it, if you have a set of data that needs to be sorted and referenced to itself, and you at any point want to say grab a collection of things that are all within the same sort of like numerical order of each other, The cons, however, is that, yeah, AVLs are kind of annoying to program, as it turns out. Like, all of the fun of linked list pointers with all of the joy of recursion, always a good time. And you have to take up a little bit of extra space for that height field in each node. And so here's one thing, is that asymptotically, it does take a little time to do those rebalances, and also instantiating all of those recursive methods you'll find also take time. Though we think of calling a method as the same sort of logarithmic runtime as another iteration, remember there's that sort of distinction between theoretical asymptotic analysis, which is just like all commands count as one magical unit of something. And I think I've sort of joked, like, that's an instruction. That's technically a clock cycle, maybe. But actually creating an instantiation of a new recursive call, closing those recursive calls, if you actually timed it on your computer, you would find would take a little bit of extra time. So it sort of depends on what's important to you performance-wise. I think that's the end of my conversation on AVL trees. Does anybody have any final AVL questions? Yeah.
Question: if we use AVL to store data, is it each time we add data into it, we need to just sometimes we need to kink it again and again, and we continue to add data to it?
So every single time you add a piece of data to an AVL tree, you need to go find where it belongs based on the binary search property, and then you need to ask yourself, should I rebalance this thing? And then do the rebalancing right then and there. Is that what your question was? Yeah. Yes. So at the moment of insertion, you just immediately handle that stuff. So it's the insertions that incur that little bit of extra runtime of the put and the rotations. But say the get or the contains key, that since it's not doing any rotations and you're guaranteed it's balanced, it's just going to be logarithmic time to travel that one path from the top to the bottom or wherever you're looking for your node.
Arrays or map to store and change data if we use AVL, since every time we need to use key?
So I would say if you're comparing map implementations, an array map where you don't necessarily have any hashing or anything like that, like Project 2, right? You have to run that a linear time to find something, which is really annoying. So I would say array map pretty uncommon, except in using it to create a hash table. Am I right? Project 2, yeah. Other than that one, I would say usually when you're kind of deciding between different map implementations, and you may have encountered this in 143, you tend to come down to either a choice between hash map. Hash map, remember, that one is one that will give you the quickest put and the quickest get, because it's not even logarithmic, right? It's like sort of constant. AVL, keep in mind, won't maintain the order in which you added things. That's usually the big loss with hash table, right? Because once you do a hash, they're like, we don't care what order things are coming in. It's going in a certain place. AVL also will not remember the order in which you added things, right? Because it's going to go into the tree in a certain spot. We're going to rotate, all of that good stuff. The thing that you get with AVL is that you get that sort of like nice grouping of nodes. So you can say, I want every bit of data that's greater than the median. Then you can just sort of like take the overall route to the right. So if you're trying to find that grouping, but it does have a slower asymptotic runtime because log n will be slower than constant. Yes. Yeah.
I was just curious too, if we're making a tree of n elements,
sure,
n nodes, to create the AVL tree, would the runtime to create that entire tree be n log n then?
Yes, great question. So if I had n items I needed to put into the tree, then I would have an overall runtime of creation of n times log n, because each item takes log n times multiplied by n. So you're right. Yes. Any other AVL follow-up questions? Here is a delightful list of other self-balancing trees. So AVL is kind of the canonical example of a self-balancing tree. We talked about invariants, right? Like it has that binary tree invariant, the binary search invariant, and then the balanced invariant. Here's a bunch of other self-balancing trees that have different invariants associated with them. I would say in these, if you're just sort of like, Casey, which ones are popular? Red-black tree is one that sometimes is talked about in other iterations. Of course, it was in my iteration, and splay tree comes up. I will fully admit I hadn't even heard of scapegoat tree. I don't know what that is, but I stole this from Lillian, as you can see here. And so feel free to dive deep on these for funsies. You'll find generally in an interview or industry context, as long as you are aware of the idea of a self-balancing tree and you have this example, one being an AVL, you're pretty covered. But if you just want to explore, here's some options for you. Like my hashing stuff. I always want to give you one example and then you can continue to explore if you want. Cool. Okay, that's the end of AVLs. Here's our announcements. It's the exact same as Friday. Does anybody have any questions that have come up, procedural or otherwise, about Project 2 or Exercise 2 or, sorry, Exercise 3 or the midterm? Reminder, the midterm, the simulated midterm, goes out on this Friday. You'll have the weekend to work on it, and then you'll do your review of that between Monday and Wednesday. Yes?
You guys post the answers to the exercises anywhere?
We are not going to post the answers to the exercises because we have to reuse the exercises quarter to quarter. But you are welcome to sit with TAs at office hours or post on the ed board and talk about the results of the exercises in whatever detail you want. Also, maybe a good thing to start doing, because the TAs are going to make themselves doubly available this week, because even though Casey was like, please start early, we knew you weren't going to start early. And so the TAs have incredibly kindly volunteered to double the office hours time this week, y'all, out of the goodness of their hearts. And so there will not be TA office hours available starting on Friday and then going through until Wednesday of the week following, so the TAs can have a bit of break. And also because we will not be holding office hours while the midterm is out. We will answer clarifying questions about the midterm on the ed board, but it is up to you to actually work through the problems. Yes?
When is the grades for E1 and E2 going to be out?
E1 will be out a little later this week. E2, unfortunately, won't be out before the midterm comes out. Great questions. Yeah?
Will the midterm include any programming aspects, where we write out code?
Nope, the midterm, I will tell you, will look exactly like Exercise 3. Like literally Exercise 3 is a midterm question. However, it's an example of two separate students answering a midterm question, and then you're going to complete the review section. So for your midterm, you're going to do what the students did in Exercise 3, plus what you're being asked to do at Exercise 3. And right now, we're planning that you're going to do that for 2 questions instead of the 1. So Exercise 3 is an example of 1 question with 2 possible designs for it. For your midterm, you're going to do 2 different designs and then 2 different reviews. So hopefully it will not be a surprise. It is all design, no coding. And here's the topics for you. Any other questions? Cool. Okay. This is a bunch of slides that I honestly wish I had time to go through, but I'm just going to leave it here for you as a way to review for the midterm. It's a bunch of conversations about design stuff, and maybe if I have time, I will post about it later, but you can read it. Ta-da. Okay, here's what I really want to talk about today. We're adding a new ADT. Yay! So this is also an ADT that you may have encountered in 143. It's called the priority queue. A priority queue, what is that? It is the idea that we can insert things into an ordered set, and then when we remove things from that ordered set, unlike the standard queue, where the standard queue just maintains the order of first in, first out, the priority queue instead maintains the order of first in, highest priority out. So if it helps, I like to think of this as sort of like the triage queue. We should all hope that if we show up at the emergency room, that say a gunshot wound should be seen sooner than say a paper cut kind of thing. This is a delightful scenario that one of my head TAs wrote from back when Anne Marie became the president of UW, I think that quarter. I'll let you read it. Yes, okay, cute. Just in case you're not sure. Okay, here is the details for a priority queue. So it has the add, and the difference is instead of just remove and peak, it's remove min and peak min, meaning sort of like the next highest priority. So you could imagine really good uses for this would be, sorting algorithms, graph algorithms, printers, triaging, things like that. Technically, you did use it if you did the Huffman coding project in 143. I think they actually had you use a priority queue in that. And I think if you opened it up and looked at the priority queue, it sort of maintains things in queue order, and it's not until you call remove min that you see the order of it. Okay, most important first out. Yep, agreed. There we go. Now, here is the thing. When I say priority, sometimes that could mean the smallest thing in the queue, or that could mean the largest thing in the queue. And the reason I say smallest or largest is because we're ordering things in the queue by using the compare to method. So when you're creating an object that is going to be leveraged for this priority queue way, you need to determine what aspect of that object dictates whether it is either higher priority, meaning the larger value, or it's like the low priority comes out. So we sort of have this idea of like either the smallest thing first or the largest thing first. That's how we dictate this idea of priority. These two things are implemented exactly the same way. The only difference is the directionality of the alligator mouth in comparison the min and max. So for the rest of this course, I'm only going to talk about min priority queues, but keep in mind everything applies to max as well. You just got to swap the order of how you compare things. And I'm going to show you why I care so much about that. So let's think about how we would go about implementing this thing called a priority queue. So hopefully we know how to implement a queue using an array. So maybe we use an array again to sort of implement it. So in an array, we get that constant time add as long as there's still space left in the array. We just sort of dump it into the empty space at the back, right? To remove, though, we don't know where the smallest thing is, right? So we'd have to loop over everything and find the smallest thing. Same thing with peak. If we instead maybe like maintained a sorted list, like maybe we used a linked list to implement this, but every time we added something in, we like made sure we added it in the right location so that at the very front pointer of the linked list is always the minimum item. We can maybe kind of incur that end runtime instead of on remove and peak, we incur it on add, meaning we kind of like loop through and insert this where it belongs. Then we get that constant time remove and peak because we know it's going to be at front. In AVL, we know in that particular case, because of the binary search property, where can I find the smallest value in any AVL tree? Anyone? Where does it live? I love it. Yeah, hard left, right? Yeah. So if I start at the overall root and I just take all lefts, I will find the smallest value in a binary search tree or in an AVL tree, right? If I'm looking for the max, I just start at the top, I go all right. So that's where I get that logarithmic time to find, to the remove min and peak. And then because we just talked about with AVLs, there's that logarithmic time in order to insert something. So what if instead we sort of created a field that every time we inserted something, we checked like, hey, is this smaller than the thing I currently know is the smallest thing? Maybe I add like a field and then I can sort of return that thing. That's what's happening here. Binary search trees. Yes, I don't know why we have that, I agree. So instead, maybe I'll leave it here. This is sort of like the best case scenario for how to implement this priority queue with what we know so far. So, like many situations, we can, of course, implement the priority queue with any ADT, right? But these are a little suboptimal, right? What if we had a data structure specifically organized to make this easier for us? Introducing the heap data structure. So, in a binary search tree, we organize the data to find anything quickly, right? Like to either go left or right based on if something was smaller or larger. What if we kind of like built off of that idea that things appear in the tree according to their relative value to the rest of things? But what if we optimize that specifically to find the smallest things really quickly? So let's write a new invariant. Every node is less than or equal to both of its children, i.e., let the smallest values bubble to the top. So the overall root will be the smallest value, and any other values that are larger will become its children. And then values larger than that will become its children, and so on and so forth. So that we've got these sort of like bands, if you will, where the smallest values are at the top and everything larger than that becomes its children. Now, it's very easy to find the smallest node. We are intentionally maintaining the smallest value at the overall root. So here is an example of a heap where 4 has 6 and 5 as its children, which works totally fine. Both 6 and 5 are larger than 4. And then if we look at 6, 6 has children 8 and 373. Totally fine, because those children are larger than 6. 5 has the child of 7, which is larger than 5. However, does this satisfy, this doesn't look like an AVL tree, right? Notice we don't actually care about the left versus the right. Things are in a little bit less predictable order. So this is kind of a looser invariant, if you will. We just need to guarantee that the parents are smaller or equal to the children. Questions about this invariant? Let's see it in action. Oh, here's another delightful heap example. Does this satisfy the invariant? Yes, it does. And that should be sending some spidey senses tingling like, oh, that's usually a worst case scenario, right? So instead, we are going to add another invariant. This is going to be that fullness that I started talking about way back when. Instead of saying balanced like the AVL tree, because the AVL tree had fewer options as to where a node could be placed because of the binary search invariant. Heaps, there's a few more options for where something can go. That placement, that structure invariant of relations to nodes is a little looser, but we never want to get in that degenerate state. So in order to maintain a short tree and a good runtime, we're going to add this other invariant, which is again a little looser than the balanced invariant. What we're going to say is we're just going to make sure that the heap is always a, quote, complete tree or a full tree. And the definition of a complete tree is that every row except possibly the last is completely full, meaning before we start another layer of nodes, we have to fill up everybody's left and right at the current level. And then once that level is full, we start again, and we always fill from left to right. So, which of these trees is a full or complete tree? The tree on the left or the tree on the right? Which one is complete? Left. I agree. So 4 is a complete level. It has a left and right child. This is a level where we've got 6 has an 8 and a 9, so 6 is full. 5 has only 5 as a child, which is okay. They can be equivalent. We can have duplicates in this context. The only open space is the bottom right corner. and it's totally okay. That's the definition of fullness, because we have to have a way that we're sort of filling this up as we go. This one over here is not considered complete because we have this gap here on 6's left child. So this 9 that got placed over here on the 5, it really should have gotten placed here to 6's left. Yeah, question. It's random as they come in. I will show you how all of these things kind of get placed. But so, for example, let's say in this heap, because this one's a valid heap here, I had another value to insert. I know I'm going to jump right here to the next opening and insert it there. Yes?
So what if there was like a value that's like lower all those numbers? Then would you just make a new entry?
What if, say, for example, I tried to insert the value of 1 into this left tree? Great question. Maybe we should spend the next lecture and a half talking about the delightfulness that is how to solve that problem. So here's our invariants, just so that you recognize. We are specifically working on binary trees, so everything has to have at least 2 children. It has to have what we call the heap invariant, so everybody's child must be equal or greater than me. And then the heap structure invariant, that's the fullness. So here are some examples, and then I'm going to get to the question about what do we do in that, what happens when we insert something that breaks this apart. Let's start here on the left. Is this a heap? Yeah, I agree. Okay, what about this here? Is this a heap? Okay, cool. What about this here? Is this a heap? No. Can anyone raise their hand and tell me what makes this on the right not a heap? Which invariant does it break? Let's see. There in the middle. Yes. It's not full. Yes, exactly. Where is the gap? Which node has a gap? 2. 2's got a gap. Any other nodes with a gap? 4. Yeah, and we don't even know who, what, in what order this is. But right now, these nodes shouldn't be here. This is a gap. These, nodes shouldn't be here. This is a gap. Yes, I agree. Yes, there we go. Yeah, problems. Cool, great. Heap invariants. Okay. Oh, here. Okay, self-check. All right, go ahead. Chat for a couple seconds. Which of these is a heap and which is not? Go ahead. All right, let's see. Let's maybe start with this over here on the leftmost. Does this satisfy the binary tree invariant? Yes. Okay, cool. I'm never trying to trick you with the binary tree invariant, but computers, they like to be specific. Okay, does this satisfy the heap invariant? Does every node's children, are they equal to or greater than their parent? Can anybody see a node in this that breaks the heap invariant? I see some hands. Yeah, who wants to tell us through it? Anybody? Please. The 2 is smaller than the 4. Sneaky, sneaky. So we have broken the heap invariant. So this is already not a heap. Does this satisfy the completeness invariant? I see head shaking generally. Does this complete every level and fill from left to right? No. We also have a gap at that 2. We have a gap on those 3s. So this is not a heap. Okay, what about this thing in the middle? Does it satisfy the binary tree? Is it binary? Cool. Yeah. Does it satisfy the heap invariant? Aha! There's another sneaky one in here. Which node breaks the heap invariant? The 6. The 6 is smaller than. So if we swapped these two, then the heap invariant would be satisfied. Yeah? Does this satisfy the completeness invariant? No, it's that degenerate tree, and that's why we have that invariant. We must avoid the degenerates. Okay, finally, this one on the right-hand side, does it satisfy the binary invariant? Yes, I see shaking. Yes. Okay, does it satisfy the heap invariant? Okay, everybody was looking real closely. Yes, I agree. This one does satisfy the heap invariant. Does it satisfy the completeness invariant? Huzzah! So that is our one and only heap. There we go. Bye-bye. Invalid. Valid. Valid. Yay. So judgmental. Okay. Cool. Okay. So because of the completeness aspect, we are guaranteed to have a height of log n. Because of the binary nature of trees, as long as we are filling up trees, we are guaranteed that pretty much every time we go left or right, we're cutting the number of options in half, right? So as long as our tree is complete, we are guaranteeing a log n runtime from top to bottom. Okay. Does anybody have any questions before I really dive into this? How do we actually maintain the delightfulness of this? Yes? Yeah. So if this was a max heap, would we still sort with the smallest top? Actually, it would be the opposite, where we would have the largest at the top, and the invariant for that would be all of my children are equal to or smaller than me. So the largest number would be the overall root, and then things would get smaller from there on for a max heap. Correct. So you can only have either a min heap or a max heap. And that's what we're optimizing for, that the smallest number or the largest number is the overall root, which was what makes it super easy to find. Any other questions? Okay. So let's implement some of these priority Queue ADT functions. So peak min, where do I find the minimum value in this minimum heap? Where do I look? Overall root, boom. How convenient. Runtime, constant. Great, love it. Okay, now, how do I actually pull the minimum value out? It's one thing to find it, but then I've got this big old gap, right? Now I've got 2 branches without a trunk, right? Who can become the overall root? Where can I look for something that can still maintain the heap invariant, but take the place of where that 2 was? Yeah, we can look to my children, right? Like I know my children are going to be just the next level bigger than me, right? Actually, what I'm going to do is this very odd thing. So that is the totally logical way to think about it, but it actually ends up becoming really hard to implement that, because if I did, I would then take 4, for example, and then I would have to then take 5, and then I would have to take 11, and I would have to do all these complicated things. Instead, what I'm going to do, and this is, I guess, the answer to our question from before and the foreshadowing for what we will spend all of Wednesday talking about, is we're going to actually insert something that will not break the completeness structure. So I'm actually going to maintain the completeness structure first, and then I'm going to do something called percolations. And what I'm going to do is I'm just going to recursively swap based on values. So I instead with the AVL tree, right? Like remember I sort of like put in based on the like the BST invariant and then I rebalanced. This time I'm maintaining the completeness and now I'm trying to fix the heap invariant. So it's a little bit different. It's like the opposite of which one we're sort of like selecting for there. So welcome to the world of percolations. Percolations is the term for how values are going to either move up or down within the heap. And so in this case, 13, because it's at the very bottom of the tree, that's probably going to be a pretty large number. So what I'm going to do is I'm going to swap with my smallest child, which happens to be 4, and then I'm going to keep going until 13 finds its way to where it belongs. Now, I have maintained the completeness and I have fixed the heap invariant. Maybe I'll leave it there. We're going to talk all about percolations and how they function on Wednesday. Reminder that Project 2 is due on Wednesday. If you haven't taken a chance to take a look at Exercise 3, look now because it's a great time to ask questions before the TAs go dark on you starting Friday. Thanks so much, everybody. See you Wednesday.